from Washington University, which is in St. Louis, for those of you who don't know that. There he's an assistant professor of computer science and engineering. I know Kilian from his days as a grad student at Penn under Lawrence Saul in machine learning. And after that, Kilian went out and worked for Yahoo for a couple of years, right?
Right.
Yes. Good. You should be proud of that. He had a lot of really good papers at Yahoo. And then he is now at the University of Washington. So he does a lot of great stuff in machine learning with applications to text, images, biomedical applications. So something that I remember from his thesis is he gives really awesome talks. So like we came to the talk because the slides were so stellar, like they made a movie of it, at least on DVD. Anyway, okay, I'm gonna stop. So we're really excited to have him here today and to see what he's come up with.
Thanks, Mark. Way to set up expectations. I'm talking about learning with marginalized corruption, and this is joint work with a lot of my co-authors, in particular Lawrence van der Maten, my students Min, Stephen, and Fei Shan from USC, Alice Sheng from Microsoft, and Ryan McDonald from Google. And my talk is in 3 parts. The first part is the longest. It's significantly longer than the other two. The third part is only a few slides. And first I will introduce the concept, what I mean by marginalized corrupted learning, or learning with marginalized corrupted features. And then the second and third part are going to be about how to use that in applications. And hi, Jason. And feel free to interrupt me at any time. All right. So I'm a machine learning person. And so before we get started, I just want to say, so I view machine learning kind of as a general tool. So if you when I talk about machine learning algorithms, you could imagine I'm using those for text data, for example, to classify documents by topic, or classify documents by sentiment. But you could also view that as image classification, for example, classifying images by their content. Is there, building a car classifier or something like this, or have speech data or something like that. So I'm not restricting myself to any particular type of data. And in terms of my framework for learning, I focus on empirical risk minimization. Kind of a quick poll. Who is familiar with empirical risk minimization? Raise your hand, please. Okay, awesome. Good stuff. So basically, it's a very general framework of machine learning. And it basically just views machine learning as an optimization problem. So you basically this is my optimization problem. I have a minimization. And I minimize over a loss function. This is my loss function over my model parameters. And later on, I have a model that's parameterized by these W here, my parameter vector. And that gives me predictions. And there's a very general framework. For example, for vector machines, can be written as this, or logistic regression, ordinary least squared, etc. And even neural networks you could write as such a framework. Let me just talk about the different parts. So here you have 2 different parts in your minimization problem. The first part is the loss function. And what the loss function does, it really just measures the error that you're making on the training data set. So because the error that you're making on the training data set is a non-continuous function, so the loss function is basically some kind of upper bound on this error. And if you drive it down to 0, then you typically have 0 error on your training data set. So you want to minimize the loss function. Typical choices are the exponential loss, very common in boosting, quadratic loss, or the log loss if you do logistic regression. You can just plug those in. The second part is the regularizer. And the regularizer, what it does, it trades off bias versus variance. So let me just explain this. So later on, once you have the model and you employ this in the real world, you're going to make some error. And that error decomposes into exactly 3 parts. Part of the error is because you have noise in your data, and that's just the way it is. And the second 2 parts are bias and variance. So bias, is the error that you're making because your classifier, from the beginning, had a preconceived notion of what your data should look like. So for example, if you have a linear classifier, your classifier believes that there's a line that separates positive from negative samples. No matter how many samples you give it, it will always think there's a line. So that's a preconceived notion. It's a bias towards a certain kind of decision boundary. So if you have high bias, that basically means your classifier is not flexible enough for your data. And if you have high variance, that's exactly the opposite. That means your classifier is too gullible. It basically overfits to the training data. It basically believes things in the training data that don't generalize to the general case. And what the regularizer does, it trades off variance for bias. So basically what you're doing is you reduce the error that you're making due to variance, and you increase bias a little bit. And there's some kind of sweet spot that's the overall minimum usually. And what's fun? Oh, okay. And so typical choices for the regularizers are, for example, the L2 norm or the L1 norm. And what does that mean? So if I stick an L2 norm here, I'm also minimizing the norm of W. What I'm really doing actually is I put a circle in the space of all possible parameters. So in this, these are my W1, the different dimensions of my classifier, model parameters. And I say it has to lie inside the sphere. And that's almost an arbitrary choice, more or less. But it introduces bias. Basically, I'm saying, I have a preconceived notion what my model parameters should look like. They have to be inside a little ball around the origin. Right? And this way, I'm actually reducing the variance that I have. The same thing with the L1 norm, you actually lie inside this kind of diamond. And I claim actually that the trade-off, the bias-variance trade-off, is probably the most, or arguably the most important topic in machine learning. So most of the problems that I see in the real world, people applying machine learning on some data, come from the fact that people don't really understand the bias-variance trade-off. And that's actually not surprising. But by the way, if you're Bayesian, or if you prefer the Bayesian view, this here is actually just the prior over your model parameters. Right? So if you take the log of that, then you actually get some kind of regularizer. So, and so it's not surprising that that's kind of a source of errors. And the first reason for this is that the models are actually quite sensitive to that. So it's not so obvious what your best regularizer should be, and more important, you have a constant here, how much you weigh it, lambda, what exactly to set that constant to. The second thing is that these norm-based regularizers are typically quite arbitrary and are not, there's no good reason why exactly it should be 0 other than mathematical convenience. So almost certainly the perfect classifier will not be in that ball. There's also side effects. So for example, if L1 regularization gives you sparsity, etc. And that for someone who's not actually, for people who do machine learning their whole life, that's easy to understand. But for someone who doesn't, that's always very counterintuitive. And most importantly, actually, if practitioners, people who use machine learning, they usually know everything about their data. So that's, if I talk to a biologist who use machine learning, they know everything about, where the gene expression data comes from, etc. They can recognize abnormalities, etc. But they don't have very good intuitions about model parameters. And what you're doing in regularization, you're restricting your model parameters. You kind of put some prior intuitions about your model parameters into your optimization. And, most people don't really know what model parameters should look like. If I talk to biologists and say, well, what do you think the weights of an SVM should be on this data set, right? They usually don't know. How would they know? But they know that data inside out. So my claim is in some sense, well, couldn't we do better? Couldn't we, instead of regularizing based on model parameters, which are very abstract, or by regularizing again, you could also imagine like putting priors in model parameters. Couldn't we instead somehow incorporate the knowledge of the data, which most of us actually understand very well? Right? If you're someone who does speech recognition, for example, you probably have very good intuition about speech data. Right? But it might be more abstract to actually come up with good priors over some models.
So this is the intuition beyond serial regularization?
Yeah, that's right. But it will be different in a minute. Like, I'm not saying this is now. I'm not inventing this, right? Yeah. Well, that's exactly right. So let me go back to the root of the problem. Why do we even need regularization in the first place? And the reason we need regularization in the first place is because we don't have enough data. If we had an infinite amount of data, infinite amount of labeled data, then we could actually, we could just take our loss function, just minimize it to 0, or as close as we can, and we can make our model as complex as possible, and we do very well. Right? In fact, people do this. That's in some sense why deep learning is so successful these days. Right? So we have very large data sets with many, many labels. So you can have a very complex deep neural network and train that over that data set, and you actually do very, very well. Right? But in those cases, people typically do not regularize. So there's a little bit, but very little. So the problem is that we don't have enough data. Now, typically our data comes from a distribution D, and if the distribution is known to us, well, then we could just sample more data, and we wouldn't have a problem. So typically, the distribution is not known to us. So the data could, for example, be the distribution over all, pictures of cars, right? So you can sample, a data point there. You can just go outside, take your camera, take a picture of a car, but it takes effort and time, and you can't do that a million times a day. So you're somewhat limited. So what I'm proposing instead is to define a new distribution D prime, which I know exactly what it's like because I made it up, and sample data from that distribution D prime. And because I know what it's like, I know what that distribution is, I can actually sample as much data as I want from that distribution, infinite amount of data. Let me formalize this a little bit. So instead of regularization, what you come up with when you have an optimization problem, when you have a machine learning problem, you take your data set, and then you come up with some new distribution, and I call this corruption, which is my distribution D prime, which, let me just show this. So basically what I'm doing here, I'm taking any given data point, and I'm sampling new points around it. And I call this corruption. That's my distribution D prime. And the support of that distribution is basically the same as my original data distribution. So let me give you an example. Imagine I have images of cars, right? And maybe I've collected a couple thousand. That's not enough. But I can do one thing. Imagine I take this image here and I remove some pixels. So I set some features to 0. Right? Well, most of you, I guess everybody in this room, will still recognize that this contains a car. Right? So I corrupted it, but the label actually didn't change. So if you take the human beings as a benchmark, then we know that this is still learnable. Right? You can still actually recognize the car in here, despite it's actually now a different picture. So this is my corruption distribution. I take the original image, and I corrupt it somehow. I get a corrupted version from it. And these are different distributions that I could use. For example, this here is blank out. This error should go from blank out. But just set some features to 0. So these features here were just set to 0 randomly. Another distribution could be Gaussian noise. Right? I just take my images and I just add Gaussian noise to them. Right? And you can still see the building here. This is the library at the UCSD school, university. Or another distribution could be Poisson distribution. So let's say I have a bag of word vector, and I have term frequencies, so how many times a word appears. Each dimension here means how many times a word appears in a document. This here is, let's say, a movie review, and 5 times I have the word amazing. Right? So that's probably a good review. If I do Poisson corruption, that means I stick that in a Poisson distribution, and this is the mean of the Poisson distribution, then I actually get some count around 5, so I might get 4. Right? One of the reviews has only 4 times amazing. It's still a positive review, I would say. So the intuition is, you take your data that you have, you find out data that you have, and you corrupt it with one of, with a given distribution. And I claim it's much more fun, or more intuitive, than corrupt your data, than to come up with some priors or regularizations over your model parameters. Let me go through this in an example. So let's say I want to build a movie, sentiment analysis system where, I want to, given a movie review, I want to have a classifier that tells me is that review positive or negative. So what do? I go to Amazon and I get go to some movie, Pulp Fiction in this case, and I download a couple of reviews. So here I have 2 negative reviews, these red stars, and 2 4-star positive reviews. And I would like to train my classifier on that. But that's not enough data. Right? So let's imagine for now, I can't get more data. So what do? I just duplicate my reviews multiple times. And in the duplicated versions, I then randomly remove words. This is kind of like the way a letter looked when you send it to East Germany or something. Right? The East German government kind of removed some words there. So each word, you just remove with probability Q uniformly. And now you use this as your training data, right? And now actually, instead of just having 2 negative reviews, or 2 positive reviews, I now actually have 6 of each. And one thing you might realize is, actually, there's no reason why I can only do this twice. I can do this as often as I want. So I can actually generate as many reviews, as many data sets, as many data points as I want from this new distribution. Right? There's 2 to the m possible reviews that I could generate out of one review, where m is the number of words. Any questions at this point? Yeah.
So in our case, this makes a lot more sense because it's clear when you look at the image, it's about the fact that it's a car. So there's
You're exactly right. So basically, I could just be unlucky and just, I just remove all the positive words in the review, right? And so my hope is that I'm doing this often enough, right, that only happens very rarely. But you're right, right? So my assumption's not, I'm assuming that I'm not changing the label, which is not always the case, right? Or, in one extreme case, actually, I'm removing every single word, right? That's very unlikely, but it could happen, right? The probability of q to the n. And then actually you have nothing left, right? But, if you do it often enough, most of the times, actually, you probably won't change the review.
Do you want comments at this point, or hold those to the end?
No, only questions. Yeah, okay. Yeah, I mean, I will continue a little bit more in depth if you... Okay, yeah. So, this actually is a great idea, and turns out it's not a new idea. It's been around for a while. In fact, Chris Burgess and Bernhard Schulkopf came up with this in 1997, and they called it virtual support vectors. So they, back in the days, basically took m-list digits, so this digit recognition, and they just translated them a little bit and got new data this way, and just showed that actually if you train on this transformed data, you actually do a lot better. But let me just write this in terms of empirical risk minimization. So here's my new updated loss. I sum over all n data points, and for each one of them, I sum over every single corrupted copy. So I have m corrupted copies, and I minimize the overall loss. And here by tilde here, x tilde is the, but I didn't introduce notation earlier. So x is my document, y is the label, and these are the parameters. So this is my corrupted, the jth corrupted version of document I. So for each data point, I get m corrupted copies that I then stick into my loss function. We can try this. So this is actually a data set that Mark Dredzy collected several years ago. The Amazon Amazon data sets, these are actually movie reviews, I think, or I don't know what it is. And so if you just train it with this L2 regularization, you get 18% error. And now if you add corrupted copies, then one thing you see that the error goes down very, very nicely. And so, and in fact, it goes down from 18% error to 14.5. So the good thing is this really, really works. Yeah.
Sorry, for each point on the x-axis, did you choose the regularization?
Yes, by cross-validation. Yeah, absolutely. So we added L2 regularization, and that's right. The lambda was chosen by.
And the lambda was chosen separately.
That's right. Absolutely right. Yeah. So this is a competitive. Otherwise, it wouldn't be competitive. Yeah, this is a competitive baseline. So the good news is this really works, right? This is really cool. So it's really easy. And as you add more corrupted data, it goes down very, very nicely. The bad news is this here is a logarithmic axis, right? So you have to double, if you keep going down, you actually have to double the number of corrupted copies. So you actually need a lot of corrupted copies. So at this point here, I'm actually going over my data set 256 more times than I did originally. That's a,
well, in particular, if I cross those bars, there's no difference
from 32 to yeah, I guess it goes down a little bit. It will go down a little bit further, actually. Yeah. So I guess you have some bar here. You're right. Here the bar becomes very tiny, right? Yeah. Yeah.
So I don't understand. You have another regularization parameter, which is the nature of the noise that you're adding and what the variance of that noise is. I mean, if I have an image and I add.
So that was also chosen by cross-validation, like the amount of there's a parameter q. How likely is it that I drop a word randomly? And that was also chosen by cross-validation. Yeah, this was a grid search over 2 dimensions, lambda and q. Yeah. And actually, the one thing you can actually see that here at this point, if you have a lot of corrupted versions, actually the original regularizer gets a very tiny weight. Basically gets switched off by cross-validation. Okay, so what I'm trying to convince you here is that this is a really good idea, but however in practice is not very, or at least it's slow, right? Because you actually have to go over your data many, many times. Ta-da! Our solution is marginalized corruption. So, and it's a very, very simple insight. Basically says, if I take this formula that I just showed you, and I let n go to infinity, so I basically have a lot of possible corruptions, right? As many as there are. Then this here becomes exactly the expected value of the loss, right? By the weak law of large numbers. And so I just, instead of using this and having the explicit number of corruptions that I use, I just let n go to infinity, and there's no overfitting, right? Because I'm just adding corrupted samples. I'm just adding more training data. So that's not a bad thing. It's only good to add more data. And then I get the expected value of the loss. And so the question is, well, have I gained anything at this point? Well, more explicitly, can I compute this expected value? And if the answer was no, this would be a really terrible talk. So the answer is yes. And in fact, I can compute it in closed form. So given two assumptions, A, your loss function is either quadratic, exponential, or the log loss. There's a little asterisk here. And second, there's some mild assumptions on the corruption distribution. And I will talk about those in a minute. And closed form, of course, is, it's super, super fast, right? So instead of going over my data many, 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 many times, I can just, it's just a little bit of algebra. Let me show you an example. So here's a quadratic loss. So quadratic loss is basically, I just have my text document or whatever it is. I compute the inner product, and I take the square difference from the original label. I take the expected value of this under the corruption distribution. That's our change. You can push that through, and I'm not going to go through the math. But the nice thing is, as it is the case with the square loss, you can actually find a closed form solution for the parameters. Because the parabolas, you can just jump right to the minimum. This here is the closed form solution. And the beautiful thing about this formula is that it actually accesses the distribution that we use for corruption only in two ways. With the expected value and with the variance. So it's actually well defined for any distribution that has a finite expected value or has a finite variance, which is a lot of distributions, right? So when I said mild assumptions, I really mean very mild assumption, right? It's not a big deal. And so, the examples that I gave earlier, blank out noise, where you just take a feature and just randomly set it to 0, bit swap noise, Gaussian noise, Laplace noise, Poisson noise, they all have finite variance and finite mean, so we can just plug them in. You can now go back to the data set that I just showed you and actually run this. And so basically, if we go over a data set infinitely many times, we see another drop in error. We go actually from 18 to 14. But now it's actually a lot faster, right? Because we don't have to go over our data set repeatedly. We just go over our data set once. So it's way faster than these points here. I can give you another example. So the exponential loss. So if your loss function is the exponential loss, it looks like this. So it's this e to the minus the label times the inner product. You have the expected value of that. Now, one thing you got to notice is the inner product is really just a sum over, these multiplications in of the different features. So, if you take the e to the sum, actually that's a product of exponential variables. So you can just pull that out, and now you get the expected value of just this term for each dimension. And at this point, you can't push the expected value any further. But if you remember from statistics, that actually is a good old friend in statistics. That's actually the moment generating function of this distribution. And that's awesome because statisticians actually have, for 100 of years, computed moment generating functions for all sorts of distributions, right? So certainly everything in the exponential family has a pre-computed moment generating function. So what you do is you just type moment generating function to Google, and here's the Wikipedia page. And for all these distributions, and this goes further down, the moment generation function is pre-computed, right? So you don't have to do anything. You just plug that into that equation. And that also means has a mean and variance. So here are some examples. So blank out noise, again, these are my running examples. This here is the moment generating function. Again, Poisson distribution, this here is the moment generating function. And I just plug that in for the expected value. And so one thing that's kind of nice is if you look at the Poisson distribution, this just uses the feature value and the label and the weight, so there's no new parameter. So in some sense, we are regularizing without actually introducing any new hyperparameters. And finally, also the exponential loss is convex to begin with, so it stays convex if the moment generation function is log linear. So that's, for example, the case for Gaussian, bit swap, or blank out. No, not in Poisson. Like in other ones, yes. Right? So here you have blank out, you have probability Q, but Poisson you don't. So that's why Poisson is really neat. There's no reason not to do it, I guess. Okay, finally, the last distribution, loss function I'm going over is log loss. this logistic regression, it's really the same thing as, the exponential loss, except that it's a log in front of it. So it's kind of, if this here dominates, then this here just becomes log of x, and this is actually a linear kind of function. So this here is the function plotted. So it's a little milder than the exponential function. It's not quite as aggressive. In this case, we can't do the same trick anymore, because the expected value of a log is actually, we can't push the expected value into the log. But we can use Jensen's inequality. I don't know if people are familiar with this. It's a old machine learning trick. So Jensen's inequality just says, well, the expected value of log of a function is less equal than log of the expected value of a function. So if we just do this, we get an inequality here. And now we have the expected value exactly where we want it to be. Again, this is our moment generating function of the distribution. So it's really easy. And this is an upper bound, but it's not kind of a, in learning theory, sometimes you get these upper bounds that are, beautiful, but, very, very high. No, this is actually an upper bound you can really minimize. And I will show you in a minute. You can just take the gradient of this function and minimize it, and you get, very good results. So again, basically, for log loss, all you need is a distribution that has a moment generating function. Okay. Let me just show how to use MCF in practice. Let me just quick summary. So if you want to use MCF, marginalized corrupted features, that's what it stands for. The first thing you do, I stole this from Apple's homepage when you buy an iPhone. You have to pick the carrier, then you have to pick which color you want, and so on. So here's, the first thing you do is you pick which loss function you want. Then you pick which corruption distribution you want. And there's way more than these three, right? They didn't all fit here. And then you get a loss function. And that's all you need to do. So let me give you an example. Let's say I'm picking actually exponential loss with blank out noise. So exponential loss is this function here. I'm taking what MCF does. It takes the expected value of this term. I substitute that for the moment generating function of the blank out noise, which again I can look up. It's just, it's all done for you already. And then I just combine these two terms into a loss function. And this is now my loss function that I'm minimizing. So instead of minimizing this function, I'm minimizing this function. And that's differentiable. So you can just do conjugate gradient descent or whatever your favorite minimization function is, minimizer is, and just, drive that down until some stopping criteria is met. Any questions? Yeah?
Often, let's say in speech or in vision, right? I mean, you're dealing with situations where you're training in some clean environment and then you're testing in some other environment where you actually, it is actually corrupted by noise.
Right.
And so here you're sort of using sort of this artificially introduced noise to regularize, but then you could also be in the case where you actually have noise at test time, like noise at test time that you didn't see.
In fact, that's
Coming good.
Yeah, no, actually, so I took that out of the talk because I thought people in NLP might not care about it. But we did experiment on this, absolutely, and it's actually called the nightmare test time scenario. That you train in a distribution, and then during test time you actually have additional noise that you didn't have during training. And it's perfect for this, right? Because basically what you're actually doing is, in some sense, you can view it, another way of viewing this is saying you're adapting your training distribution to the test scenario, right? But you assume some prior...
Well, assuming you know the...
That's right. That's exactly right.
This would still help to some extent, even if the noise type weren't matched.
Yeah, you can approximate. You're basically approximating it, right? And actually another scenario, for example, where you have this is in search engines, where you basically have some features, there's some guarantee that the search result has to come up with 0.2 seconds or something. So if the feature is not computed in time, then actually it just dropped. So it's actually exactly blank out noise. During training, you don't have that because you have all the features pre-computed. During testing, they just drop. Same as a sensor, for example, in robotics can just fail, right? So yeah, so that's absolutely right. And by the way, one thing is for different features, you can use different distributions. I didn't go into this. But you don't have to have one distribution for everything. Yeah?
Did you assume at some point that the corrupting distribution is factorial?
That's right. It factors over. Yeah, I at the very defined this, the way I defined it, but I didn't say it. You're absolutely right. It factors over the dimensions. So for each dimension, you can pick a different corruption distribution if you want to. Yeah?
So the way you started to motivate the talk is like you don't want to, it's very hard to have an intuition about priors.
Right.
But people know about how to corrupt the data.
Right.
But now it seems to me that you're going back to, because you can argue that this is as complicated as it.
Well, no, but you don't have to know these things, right? All you have to know is what kind of corruption do you use. Then you look up what the look on Wikipedia what the corresponding moment generating function is, right?
But my corruption, I don't know, it's gonna look like any of.
Well, just think about it, right? So, for example, for text data, right? Blankout noise actually is very natural, right? So, for example, you imagine a word is suddenly not there during testing. That could be for various reasons. For example, the author during testing might use different words to describe the same thing, right? Words, or let's say you have a review during testing where someone swears a lot, right? And those swear words actually, they don't have them during training because you have a clean data set during training, right? So if you use a dictionary, those words would just not be there, right? So they're basically blanked out, right? Or a Poisson distribution basically would say you just change, people, tone down a little bit more, less enthusiastic, a little more enthusiastic, right?
I just find it hard to think about those equivalents in like reverberation.
Yeah, so I agree. So
Machine gun noise.
Well, so one thing you could do is you could just corrupt it and see if it still looks natural, right? Okay. Any more questions? All right. Also, one question is, how complicated is this? Well, so this here is an example where I used the standard quadratic loss in MATLAB. It's 4 lines of code. This is without MCF. This is just with L2 regularization, I think. Yeah, here's the L2 regularization. If you use MCF with Poisson, you're adding exactly 1 line of code. Right? So in terms of coding it up, it's really, really easy. And if you use blankout corruption, well, you're adding 3 lines of code. So it's really, there's very little reason, not to try this, I guess. How does it work?
But that MATLAB code is for linear classifiers?
There's linear, yeah, right, good point. At some point I switched to linear classification, yeah. So you could pre-process your data to get non-linearities. Here's the Amazon review data set. That's actually Mark Dredzy's. So here we have a bunch of reviews that we classify by sentiment. So is this a positive review or a negative review? We have books, DVDs, electronic equipment or kitchen appliances. And this is the same graph as before. What you see on the x-axis here is the amount of blank out corruption. So this is basically the probability that I remove a word at random. And the point here, basically, the starting point is basically just having 0 corruption. This is just normal linear classifier with L2 regularization. And then as you go to the right, you basically start to corrupt more and more and more. One thing is, unfortunately, here, I do have the plot now, but it didn't have it at the time, is that if you keep going to 1, then actually you see the error shooting back up again. Right? So if you have actually 1, that means that every single word is corrupted every single time. So you remove the entire document. So you have 50% error. Right? So just you actually see, just as a sanity check, if you go up here to 1 again, it shoots back up. But there's a few things to notice. One thing is, it helps very, very nicely. The lines here is blank out noise. These dotted lines are Poisson noise, which have no parameter. And the other thing is it's relatively flat. So actually, if you would, don't want to do cross-validation, you just use 0.5 as your rule of thumb, you actually do pretty well. Right? So it's relatively robust. Another thing is here we use have the DMOS web pages, and we classify them by categories. And here we again use blank out noise on the left and Poisson on the right. Again, the solid line is MCF regularization. The dotted line is just normal, only L2. And the x-axis here is how much training data we have. So one thing is often with these methods, that improve your classification results with the regularization. They help a lot if you have very little training data, but if you have more training data, they're not worth it anymore. And so we wanted to test this. And here we go up from 100, this kind of logarithmic axis again, all the way to 7,000 documents. And you can see that's actually the gap between the two, actually in this case even widens, but actually stays pretty constant at some point, right? So even with 7,000 training documents, you're still improving. Right? So it still helps to add more, in some sense, infinitely many of these virtual documents. Another data set here is image data set, a CFAR data set, a SciFAR data set. Here we have images. We classify them by object in the image. Again, here's our results. And the best result is actually obtained with MCF, Poisson corruption. That's nice because there's no additional parameters. There's nothing more to tweak. And the other thing to notice is that actually, in all cases, corruption just generally always helps over not corrupting. So
Just to be clear, the Poisson MCF corruption on the image, is taking the RGMV values for each pixel.
No, very good point. Visual, we have visual bag of word features as defined by a recent paper. This is actually the state of the art, and we use the same features. Yeah. It would not make as much sense. I used that earlier, but actually you wouldn't really want to. You always want to use some interest points or something. Yeah. And actually, so last NIPS actually, I went out to a bar with Ryan McDonald from Google Research, and after a beer, I told him about this idea and told him, you should really try this. He actually remembered it, so a few weeks later, he sent me an email saying, hey, I put it into the Google part of speech tagger, and actually it really works. And so I said, awesome, let's publish it. Well, actually, the dataset was proprietary, so he wasn't allowed to release it. But he ran it over some part of speech tagging dataset, where he basically is a domain adaptation, where he goes from news to blogs, or from news articles to chemical descriptions. I think overall he has done 9 experiments. I picked 4 actually randomly. But one thing you can see here, this here is the baseline. The red line is explicit corruption. So if you actually just take every word and just explicitly remove it with some probability Q, this here is the probability. And the blue line is actually MCF. So again, you can see around 0.5, actually every single time there's a substantial improvement, and actually there's an improvement over explicit corruption as well. Yeah?
I'm curious about this. Something I've been wondering through this talk. So if you remove a word, the labeling of the part of speech task changes.
So in this case, actually, we didn't use, let me just get this straight. How did we do the corruption? We just removed some features, actually, randomly.
Okay, so you're not actually looking at the image of the input signal under some of your feature extractor.
That's exactly right. Yeah.
So then my question, and this kind of gets to my question. It could be that once you corrupt that image, then the output that you're trying to predict is not valid for the pre-image of the corrupted feature vector. Does that?
So I think that goes into the question that was raised earlier, that we actually changed the label, right? By basically, and the reason is because you're doing it infinitely many often. It just it washes out basically, right? That's why it still works. If you would just do it a couple times, you could be unlucky, right? And yeah. Okay, any more questions? Okay, good. Second part is we actually use this for deep learning, or kind of pseudo deep learning. Who's in this room has heard of deep learning? Can I close? Okay, awesome. So it's the same as neural networks. It's just a new term, fancier term.
Before you move on, maybe this is a good time to make the connections to other things. So first of all, I've been saying for years that one way to understand SVMs is by saying that you want to not only classify correctly each training point, but also a ball around it.
Right.
And you can interpret that as a kind of marginalized corruption, right? Now, the distribution that you want in order to make it exactly the same is not Gaussian. It's something that actually has to put more mass toward the outside than to the inside because of the way that you cut off.
Right.
If you're doing soft SVMs. But it's still essentially, I think, the same idea.
It is, actually. And you're actually not just SVMs, right? So basically, if you look at the learning theory results for L2 regularization, for example, right, the way the argument usually goes is basically saying, well, let's perturb the data points. So you want to have a classifier that stays stable, right? And so you basically kind of, you say, well, even under perturbation, actually, this will still work, right? So I think in some sense, basically, the idea is, for some reason, people haven't really incorporated that into the learning algorithm explicitly. But you're definitely right. Like the margin, in some sense, does exactly this. Right? It gives you some wiggle room for the data points to change. And the assumptions during test time, you might get slightly different points around that one point. And that's, in some sense, why you get improved generalization.
And it may be that this is why SVMs get much better bounds than the DC. Get much better results than the DC bounds would suggest.
That's probably right. Yeah.
There are 2 other connections that I just want to make quick.
Yeah.
So one is the stuff you were doing with part of speech tagging, because what you're doing is removing binary features. Is this like a marginalized version of dropout?
This is a very good point. So Jeff Hinton just gave a talk at NIPS they basically said, one way to make neural networks overfit less is basically by just randomly setting weights to 0. Like actually nodes in the middle to 0. And that's exactly right. So basically, in some sense, we're doing exactly the same thing, except that we are marginalizing out. However, you couldn't do that in the internals of a neural network. And that's actually what we're getting to now. So as we're doing deep learning. And you will see this in a minute. We actually have to remove the middle layers. Right? Yeah, yeah.
And so
Actually, it's a little unfortunate because we called it blank out. And I think now, because Jeff Hinton is much, because now it's called dropout. So we have to change it to dropout now, actually, I guess.
So the other comment is that in general, when you have a finite training sample, if you have some model that you think that sample may come from, instead of doing empirical risk minimization, you can try to reconstruct what you think the true distribution over XY pairs is, and try to and then try to minimize not the empirical risk, but what you might call the imputed risk over that distribution.
Yeah, and then
I think what you're doing is really a kernel density estimate over the XY pairs, where you have a very narrow kernel on Y, so you're not corrupting Y, but you are corrupting the X.
I think you can definitely see it that way. Yeah, absolutely. Yeah, and in some sense, so what you're suggesting, in some sense, I claim it takes a lot more knowledge in terms of machine learning to actually build these. I feel like this is a very simple, a very simple modification that I hope people can actually use who know very little about machine learning, right? To basically just use an out-of-the-box method. You just plug it in, you choose your distribution, and then you run it. But you could also make a generative model or something, right? And actually, I think there's many other ways to improve your generalization of your classifier, right?
Well, I wasn't suggesting changing the method. I was just saying this is one way to justify what you're doing. So you're talking about it as corruption.
Yeah.
I think of it as imputation of other examples that you think might have showed up but didn't actually.
Oh, I see what you're saying.
Under a kernel.
Yeah, no, that's fair. That's totally fair. Yeah, that's totally fair. That's right. And actually, so here comes, okay, as you're saying this, you can view Poisson distribution that way. So in some sense, Poisson distribution, what you could say is, let's say you have a bag of word vector, and you normalize it, you have a distribution over words, and now you draw a new vector based on that distribution. Where you actually say, each word has a probability, and you draw again m words. And as m goes to infinity, you actually do exactly that corruption. Yeah. Okay, good. All right, so second part, this was actually published prior to that. So in some sense, we first came up with this, and then we kind of thought about the general principle, which is MCF regularization. All right, so let me just talk about a particular problem domain here in this case. It's domain adaptation for sentiment analysis. And I'm sure people are familiar with this, but basically, it's a big industry to go through the web and look at blogs and say, are these blog entries positive or negative, right? So companies that release a new product want to know what does the blogosphere say about my new product. And the problem is, might not have that much data on that particular domain, but you have a lot of data. On Amazon, where you have reviews and you have exactly a star rating, so you know exactly if it's positive or negative. And this is the same data set that Mark collected a couple of years ago. So the goal is to train a classifier on this domain and then basically test it on a new domain, right? Or train it here and test it here. Typically, if you just use the naive approach, with document classification, you use a bag of word model. That's what people usually do. You have a text document, and then here in this room, everybody's familiar with this. You make a vector out of it, it's the bag of word vector, and then you stick that into a SVM classifier. I claim that actually usually does not work if you go from one domain to another. And why is that? Well, it's quite intuitive, actually, that people use domain-specific language. So there's some words that actually, for example, if I say, this is my favorite book, well, this is a positive word. It's also a positive word for other domains. If I say, this is my favorite toaster or something, right? But if you say, this is very eloquent or best written, well, you can't really say that about a toaster, right? You can't say a toaster is eloquent, right? It makes no sense. The same way you can say, this has good battery life, right? It's a positive word that doesn't make any sense in books. So if you train on books and test on electronic equipment, your test error goes down quite a bit. So because you have source-specific and target-specific words that you don't capture correctly. In fact, you can just test this. So if you train on words and test on words, you get 15% test error. If you take the same classifier and test it on electronic equipment, it goes up to 26%. So it almost doubles. And so as I said, I blame the representation for this. Recently, people have looked into taking unlabeled data, which you have a lot, and learning a representation, and then taking really little labeled data to, under that new representation, stick that into the classifier. In particular, I think the most successful approach, And the world record on this data set is actually by Yosha Bengio's group, denoising autoencoders. And what they do, well, you will look very familiar. They take a text document from any domain, source or target, doesn't have to be, actually they ignore the label. Label is not important. And this will be a bag of word representation here. This here means this, this means the word favorite is present. A white dot means it's not present. And they corrupt it randomly. Each word is removed with probability Q. And then they learn a neural network to reconstruct the uncorrupted version. And then the features that they use are these hidden layers that you have in the middle of your neural network. And this method actually does really, really well. So if you look at the transfer ratio, these are different papers that have been published over the years. Stack denoising autoencoders actually have by far the lowest error. But by far they're also the slowest. They're actually, and that's because you actually have to train a pretty deep neural network, and the internal representation is no longer sparse. So the input is sparse, but internal is not sparse. They came up with some faster versions. One is on GPU, and the other one is reconstruction sampling, which is 20 times faster than just training a normal neural network. We already used that code, and it took us 5 hours for this particular data set. So again, the holy grail would be if you could get the result of SDA at much, much faster speed.
I can think of a way to get a transfer ratio of 1. Just always pick the same answer. Do the same on both domains because it would be equally wrong.
Okay. That's a fair point. Actually, wait, is that right? That's true. But actually, I will also show you the transfer error in a minute. But this is also the best. Okay. Right. So the ratio by itself is not, it cannot stand on its own. Fair enough. It's also the best in transfer error, which is then no longer relative. Okay. So you can already, or imagine what we're trying to do. Well, we want to marginalize out this corruption, right? So they basically, what they do is they go over the training data set many, many, many times, corrupt every single example, and reconstruct it. Takes a lot of time. So our idea is very simple. We just remove all the intrinsics, we got the neural network, take all the hidden layers out, instead make it linear, and then just use MCF. So we basically say we learn a matrix W that takes the corrupted document and reconstructs the original document. And this is a square loss. Square loss was one of the examples early on where MCF works beautifully, and we take the expected values, so we go over infinitely many corruptions. In comparison, the biggest difference in some sense is that they have a hidden layer that allows them to learn a couple things that we can't learn. But the advantage is we are convex, so we can actually jump right in closed form to the global minimum, and because of this, it's much, much faster as convex. And again, if you write this in MATLAB, well, it's 10 lines of MATLAB. So this here is the solution. Again, I just plug in, as we said earlier, I just plug in the expected value in this case because it's a little simpler because it's reconstruction. One thing that's nice about these denoising autoencoders in the neural network, they're actually deep. We can make ours also deep, or deep in quotes. We can actually learn a reconstruction, and then we run a sigmoidal unit, which just squashes the outputs. And then we take this new representation as the input of another layer, and we reconstruct that again. So in some sense, basically, we learn another mapping here where we say, let's take the output of our previous mapping, and now corrupt that and learn another mapping. Right? So we can just do this as many times as we want and stack it. And this actually has makes a profound difference, because what you're doing, in some sense, what you're doing here is you're learning to add words that are correlated. So to Obama, you might actually learn that there should also be White House or something. But you wouldn't learn Ronald Reagan, because Obama and Ronald Reagan don't appear together. But what you see here is let's say you have Obama, you learn White House, and then from White House you reconstruct Ronald Reagan. So you actually get second order relations. We take all the features that we learn and stick those into an SVM. And we call this marginalized stack denoising autoencoder. We can run this on the domain adaptation data set, and this is the same plot as before. Here's our graph, so actually we get the same error as SDA. One thing is you can see multiple layers really helps. And the other thing is we are actually 2 orders of magnitudes faster. So instead of 5 hours, it just takes 2 minutes. And we have the same quality representation. Here's actually the transfer error. So because someone really caught this. This is actually for the different domains. So you're going from DVDs to books, from electronics to books, and so on. And you can see the lower is better. Dark red is ours. So 10 out of 12, we're actually outperforming SDA, in fact. 2, we are doing a little worse. here we also went on a very, very large data set. This is 340, well, very large. A few years ago, very large. 340,000 documents. And, this runs in 23, our MATLAB code runs in 23 minutes. Whereas this highly optimized, autoencoder actually took 2 days and 8 hours to train. And one thing you have to keep in mind, there's a whole bunch of hyperparameters here, right, that I did not take into account. I already knew the best setting because I contacted the authors. So I only ran it once. So normally, actually, when you take a deep neural network, you actually have to set the number of hidden layers and so on, and the number of hidden nodes and step size, etc. Okay, any questions about this deep learning? Okay, now I have only 3 more slides on this. So this is currently the ICML paper that's under review. But we actually use, again, the same trick with marginalized corruption, but this time actually on the labels. And I can give you, here's the application that we have in mind. So my student did an internship at Microsoft Research, and her advisor was really interested in the following problem: giving an image, learn a mapping that actually goes from the image features to tags that describe the image. So in this case, I want from this image, I would like to go to cloud, fence, field, grass, house, tree, green sky, or something, given a finite set of tags that are possible. And so the first question even is, how do you get that labeled data? And that's not so easy, because you don't really find that on the web so much. Often, if you would just go to Flickr, the tags are not reliable at all. People load entire film rolls up and say Canada or something, and half of the pictures are not taken in Canada. But actually, Louis Van Ahn came up with a clever trick with the ESP game. Quick poll, who's familiar with the ESP game? A couple of people. So he wanted to have labeled data for images, and so he came up with this idea, basically just cast it as a game. So what he does is, this is a computer game where you can log in, and you log in and you see that image, and someone else also logs on from a different place, could be somewhere in Asia or something, and you both see the same image, and you have to type in a tag, and if you type in the same tag, then actually you score some points, and the tag is added to the list of descriptions of the image. And because the image is the only thing you have in common, the probability is very, very low that you would both, when you don't know each other, it's very, very low that you would put a tag together, that that you would write the same tag down that has nothing to do with the image. That's his idea. People actually, got really excited about this. Some people play this day and night because somehow you feel really connected with some stranger because you write in words and they write the same words. In fact, actually, once Louis Van Ahn said, some people even contacted him and said, I've been playing 12 hours of this game with the same partner, and I feel so connected. This is my soulmate. I want to marry her. Can you give me her address or something? It doesn't even know the gender, actually. But
he said he built a game mechanism that kicks you off after a game playing.
Okay, because people get too addicted, yeah. But that's great, right? So that's finally addiction that's useful. So it actually gets us a lot of data. The nice thing about this data set is it's high precision. So when there's a tag, usually it's right on. The problem is there isn't that many tags, right? So usually when you have an image, you have 2 or 3 tags. And so, for example, here you have cloud, sky, gray, but actually what you not have is that there's a huge antenna in the middle of the image, right?
Given once you've got cloud and sky reliably, you're going to put them on the taboo list, and people won't.
That's right, exactly. You cannot put the same ones in. That's right.
So why doesn't the list eventually end up with antenna? I mean, I can understand if there were only 3 things in the image, then people just continually fail on that image to generate it.
That's right. So I guess he removes it because it would. I would assume that it leads to frustration, right? So that basically he can't. At some point he takes pictures out of the rotation because a big part of he has to make the game fun, right?
Sure, I understand. But what you're
eventually, you probably would. Right. So if you would show the same image to the people over and over again, eventually they would put an antenna. And so.
And you're just saying that he cuts off before.
That's right. Yeah.
You get all the images that are in the visual research on that one.
Yeah, we would even like to have 20 or 30 tags per image, right? So that won't happen because then it would just get too frustrating, I guess. Yeah. Yeah, it's not very specific, right? That's the other thing. That's right. Okay, so so what do we want? We want to have an image. We would like to have a mapping to the full set of tags that describe the image. But during training, we're not given that. We're just giving a small set of tags. And so this here is the mapping that we want during test time. During test time, obviously, we're not giving this even. It's just during training. But this is exactly where MCF again fits in, because you can view the small set of tags as a corrupted version of this, right? Imagine someone had given, like, given someone this full set of tags and said, okay, apply corruption noise, right? Randomly remove tags. Then you get something that looks exactly like the tags that I'm given during training time. So it's just a kind of an upside down way of looking at it. So what we do is we basically do the same thing as before. We learn a mapping B that reconstructs the full set of tags from its corrupted version. And to make these two actually, agree with each other, we have a co-regularization that say these two have to agree on the same set of tags. And obviously, if you just run this, you minimize over W and B, you just set everything to 0. Right? That's a trivial solution. But we know that what does B do? B reconstructs, full tags from a small subset of tags, from corruption. So if that's what B does, then we know it should also be able to reconstruct the few tags that we have from even further corruption. So we just actually stick the MCF regularizer in here. And we train it with this at a second regularizer. This is our loss function, and we just minimize over W and B. Turns out it's jointly convex with W and B. It's closed form, so it's really, really, really fast. Here's a few examples. Here are images that we give it during test time, and you can see these are, the first row is images where we do well, high F1 score. Here you see bug, green, insect, tree, woods, right on, blue cloud. This is just the 5 strongest tags. So it gives us a whole list. It ranks the tags, basically. Here, baby doll dress, green and hair, so it's right on. Here's some randomly picked images. Again, it does pretty well, actually. Asian boy, gun, man, white. It's exactly in here. And here are some images where it does badly. So these are the lowest, these are the worst images. And you can see here this brown ear painting, woman yellow. Doesn't, So, these are kind of the mistakes it makes. We can compare this quantitatively. These are previous work on the same data sets, and the current world record is by tag prop. We're actually doing slightly worse than tag prop. So the blue line here, this here is the F1 score. We're a little below tag prop, I think, in all the data sets, in fact. But we're better than anyone else. So we kind of second place. But again, tag prop actually is quite an involved algorithm that actually learns a metric and then learns a nearest neighbor search. For each has a lot of different visual features, etc. And so in terms of speed, we're actually several orders of magnitudes faster. So here go from 16 hours to 17 minutes of training time, 15 hours to 17 minutes. And even more important, tag prop actually has, during testing, has linear. So during training, it's quadratic, whereas we are linear. And during testing, it's actually linear. So there's a nearest neighbor search. So if you're Google or something and you have a very large image data set, like from Picasa, well, you couldn't actually run this, right? Because you would have way too many data sets. Whereas we just have a linear mapping. So it's instant. It's a few milliseconds or less. So I claim that this is kind of the best algorithm that can actually be used on real data sets. OK, so finally, in conclusion, I mentioned learning with marginalized corrupted features. First, I introduced it just as a new way of doing regularization. And it's kind of a very neat trick that if you have some data, maybe try it out. It works quite nicely. Then also I talked about doing kind of deep learning or approximated deep learning for domain adaptation with this trick, and then actually corrupting the labels. And one thing that's very nice is that it works on very different, very diverse sets of data, right? And very reliably. One thing that I like particularly is that that instead of choosing model parameters, I think it's more intuitive to think about how can I corrupt my data such that it doesn't actually change the label. You just corrupt it and you see, would I still recognize it as a positive or negative example? And in the cases where, in all of these cases actually, it was extremely fast. It was faster than way faster than the state of the art. Quick last slide. So currently there's no learning theory on MCF. This is still open problems. It's not so clear. I'm pretty sure there is something to be proved here. And I thank my students and my co-authors who worked on this. Thank you. Yeah, Jason.
So I think there actually is some learning theory. I don't know this literature, but there's some papers starting with Abu Mustafa in 1995 doing pack learning on corruptions of data, and I think he was inspired by the digit recognition table transforms of the data.
I have to look that up. Yeah.
You know, where you take the image and you shift it and you shear it and so forth, and say that's still going to preserve the digit label. And so I believe there's some pack learning.
So what I believe is that it's not a big step from that to saying if you actually do this on training data, you get better generalization, right? So it's almost, I think it's very, very related, right? So I think it's either.
Yeah, so the image, the digit recognition, people were doing this stuff in the 90s.
Yeah.
You know, label preserving transformations of the data.
In fact, actually, NLP people have done blackout noise, explicit blackout noise for one, right?
Right. But I'm saying I think there actually is some theory attached to this.
Could be.
So I have a 1995 paper and a 2004 paper.
I will look it up. Thank you.
Yeah.
Actually, we will talk anyway, so maybe you can.
Sure.
Yeah.
As far as trial work, I remember a long time ago when people were still doing template matching. There was a man called Dennis Clark. He passed away. I believe it was in the 70s. And he was showing that when he added noise to his training data, it was recognized it was more reliable.
Oh yeah.
So you should be aware of this also. It was well before.
I think I actually believe in every domain people have discovered this, right? That basically, if you corrupt the data and you add more data that way, right? And actually, the world record in MNIST actually is with exactly that trick. So to be clear, the contribution here is not that we discovered it, right? The contribution here is that we marginalize it out and do it closely. Yeah.
I maybe have a related question, but I think maybe Daniel already was asking that. I can imagine that it works well for good noises, meaning like the noises which you can describe somehow. And if possible, you can describe them by some distribution.
Yeah, that's
but
right.
we very often deal with the noises which we actually cannot describe them so easily. Do you think that it would also be useful? I mean, sort of like, because example was machine gun noise, so you have all kinds of distortions on the signal which come from the, say, like wireless, or you have the reverberations. And so we all call it noise, but, but I don't think that we have easy way to somehow parameterize.
So my intuition is probably more helpful than you think, right? So for example, in our case with text, we first just tried, blank out a passant, and we realized, oh, it really works. And then we thought about it, oh yeah, it actually makes a lot of sense in that context.
So your answer is that you think it might help?
Yeah, in the same way actually that, for example, L2 regularization, right, that people use everywhere, right? If you think about it, often actually, either you assume L2, if you have a squared loss, right, you would assume actually Gaussian noise, but you might not have Gaussian noise at all. But, in practice it just helps because you introduce bias, right?
Yeah, but in your case, you're tuning a parameter for that noise that you're introducing, right?
Yeah, but in L2 you're doing the same thing, right? You basically have a lambda parameter.
Actually, Kilian, if you go back all the way to your graphs where you show different choices, like sort of in the first part of the talk, I think, you showed a graph where different choices of Q, different settings of Q, and then error.
You mean, wait?
The colorful.
This one.
Yeah, this one. So here, this is to answer Aaron's question. This is what you're on the x-axis. What you have is different choices of your parameter, right? For the noise corruption.
As a blackout corruption, right?
And then the y-axis is showing you error. So it's basically showing, for a very wide region, it's supposed to be helping.
Yeah, but here you don't necessarily have a mismatch noise. I mean, so what the speech people are all complaining about is that we have noise in test time that has nothing to do with your training data, and that it might have nothing to do with whatever distribution you assumed for your technique, right? And so if you sort of optimize for this, yes, it's flat, but now if I come in with machine gun noise, have I actually done myself harm by optimizing with respect to the wrong noise?
I see. Yeah, so I mean, in some sense, that's right. So if your distribution during test time is too different, right? Things will fall apart, right? That's just generally the case in machine learning. But so if so suddenly machine learning, if you suddenly have a machine gun in the background, that's really kind of drastic change. Right?
I mean, in some sense, you're adding this sort of very well principled extra parameter to your classifier, and that you're learning it not via an optimization, but by tuning, right? And if you
it's still an optimization, right? It's still.
Well, no, but whatever this parameter that describes your noise is, I mean, you're tuning that on your train set or your development set, right? And so if there's a mismatch now that, right. I mean, that's the concern.
But you also have that with L2 regularization, right? So you would always use a regularizer if you do machine learning, right?
That's true. I mean, so I bought that answer.
No, but I see your point. Yeah. I mean, it only goes so far, right?
So the other thing is that one thing we showed Kilian was that it's easy to marginalize in the case where the assumptions are exponential. That happened with this slide. So maybe the
Log Lawson squared, yeah.
log Lawson squared. So the other question is basically in these other cases, in each case, I think it might be interesting to see if these are actually marginalized or not.
If you use different loss functions, then it's a little trickier. I think. So we haven't explored the whole space, but
it's just a function of the loss.
it's just a function of the loss
It's a loss
function.
function, not the error model.
So the
But
error
it's
model
not the
has to have a
error
mean
model,
and a
right?
variance, so it has a moment generating
Right,
function,
a
which is
moment generating
quite
function.
minor, right? But the loss functions you have to have square, log, or exponential. That's at least the ones where we know it works. Right? So for hinge loss, for example, what you mentioned earlier, because you have a non-discontinuity, the expected value doesn't really go through it. So it wouldn't be clear how to do that. So there might be more though.
Any other questions?
Thanks for the.
All right.
Thanks.